Okay, everybody, let's wrap up Chapter 4 with Section 4.3. There's really only two ideas in Chapter 4.3 that we need to talk about. The first one is this at least one question, and the second one is conditional probability. So we're going to expand on this at least one idea in Chapter 5. This is basically a very specific question that has a very specific set of steps to solve it. And it's hard at first, but once you just do it a couple times, I think you'll learn how to do it. So it's a very specific question. So let's talk about it. If I say the words at least one, what I really mean is one or more. So if there are 10 students and at least one did the homework, then that means that 1, 2, 3, 4, 5, 6, 7, 8, or 9, or all 10 of them did the homework. And so at least one means one or more. The complement of at least one is nobody. So at least one means, like on a dice, at least one, if you rolled, for example, let's say, well, that's not a good example. Let's say there's 5 cars and at least one of them is red. That means that 1, 2, 3, 4, or 5 are red. Well, the complement of that is none of them being red. Okay? So the probability of an event happening at least once is equal to 1 minus the probability of it not happening at all. All right, so I know that's a little bit tricky. Just say that to yourself a couple times until you understand the logic of it. If there's a bunch of people and at least one of them has brown hair, then that's the same as 1 minus the probability of none of them having brown hair. Okay? So we're going to use this idea to solve a question. And we're just going to dive right into the example. So the key phrase you're looking for is at least one. If you're doing a homework problem and it says at least one, this is the procedure you need to use. So here it says, based on a poll, 45% of internet users are more careful about personal information when using public Wi-Fi. What is the probability that among 3 selected random people, at least one is more careful about personal information? So we need to calculate the probability of 1, or the probability of 2, or the probability of all 3. However, that's hard to do. And so instead, we're going to calculate the complement. Instead, we're going to do a catch-all of saying 1 minus the probability of none of them being careful. And that will be the catch-all for at least 1, meaning 1, 2, or 3. So, as I mentioned, the key phrase is at least 1. And so we can see that the probability that they're not careful is 55%, and the probability that they're not careful is 55% because that's the complement of 45%. So here's the idea. The probability of at least one being careful is equal to 1 minus the probability of none of them being careful. Okay, and that's kind of the trick you're going to just have to practice a few times to understand. So the probability of at least one careful person, meaning one person being careful, or 2, or 3, we remember that it's hard to calculate these or questions because of the addition rule, which we learned in section 4.2. So instead of calculating 1 or 2 or 3, we do 1 minus the probability of none, which is equal to the same thing. So the probability of not being careful is 55%. We are going to assume that these 3 are independent of each other, so we can just multiply 0.55 times 0.55 times 0.55. Look at this clever way of writing it. You can write it with an exponent. I like writing it this way because it's 1 minus the probability of no raised to the power of how many people you have. So this is kind of clever because it puts it all in one way of saying it. So make sure you do the exponent first, or multiply first, depending on which way you've written it. And then it'll be 1 minus that to get your answer. So if you have 3 people, and if 45% of people are careful, and if you have 3 people, then the probability of at least one of them being careful is equal to 83.36%. So that 83% is a combination of 1 person being careful, 2 people being careful, or 3 people being careful out of 3. And so we can see that the probability of none of them being careful is 16%. So that's how you do this. And I know you may have to watch this more than once because it's a little confusing. Let's do another example. Subjects for the next presidential election. We're doing a poll where we use telephone numbers. and we're just randomly picking the last 4 digits of the number. Find the probability that for one such phone number, the last 4 digits include at least one zero. So we're randomly calling phones to do a poll, and the question is what is the probability that of the last 4 digits of the phone number, at least one of them is a zero? And so what we need to calculate is one of them being a zero, or 2 of them being a zero, or 3 of them being zero, or there's one last phone number, 0000. And that's kind of tricky because the zeros could be anywhere in the number. Like if there's 2 of them, the 2 zeros could be anywhere. So how do we do that? Well, instead of doing that calculation, we just ask the question, what's the probability that there are no zeros? And then we just do 1 minus that, and then we'll have the answer for at least 1. Now, it's important to realize that there's 10 digits for a number, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 possible digits. And so the probability of 0 is 1 in 10. And so the probability of it not being 0 is 0.90. Okay? And, and what we want to calculate is what is the probability of at least 1 0? That's really hard to calculate. And so instead we do 1 minus the probability of no zeros. And this exponent, as I explained in the previous example, this exponent is the number of digits you have. And so it kind of simplifies the problem a little bit. So because we have 4 digits, that n right there is going to be 4. That's the number of digits. So we have 4 digits. And we need to put the probability in of one number not being 0. And one number not being 0 we have right here is 0.90. So I think part of the reason this is confusing is because we do one complement to get the 2 probabilities. And then we do the other big complement right here. But here's what it looks like when you calculate it. 1 minus 0.90 to the 4. And so 0.90 to the 4, you do that first, which is 0.6561. And then you do 1 minus 0.6561, which gives you 0.349, so 34.39%. So when you're calling a random phone number and the last 4 digits are random, there's a 34.39% that phone number will have at least 1 0 in the final 4 digits. And that seems like a little bit because there's only a 10% chance of each individual one being a 0. But the idea is we could have 1 0, 2 zeros, or 3 zeros, or all 4 of them being 0. All of that put together gives you about a 1 in 3 chance, 35.39%. That kind of makes sense because if you think about it, you have 4 digits and there's 10 to choose from. So hopefully that seems a little intuitive. One more example. Assume that boys and girls are equally likely to be born. Find the probability when the couple has 4 children, at least one of them is a boy. And so once again, there's our favorite phrase, at least one. And so you know to do this technique for calculating at least one. Instead, we're going to calculate the probability of no boys and do 1 minus that. So boys and girls are the same, 0.50 and 0.50. So here it is one more time. The probability of at least one boy is equal to 1 minus the probability of no boys. Or another way of saying that is all girls. So the probability of at least one boy equals 1 minus the probability of all girls. And really think about that. At least one boy means you have at least one boy. And so the complement of that is no boys, okay? Because you have at least 1 or 2 or 3 or 4. And so it's easier to calculate 1 minus all girls. And as you can see, that's 1 minus 0.5 to the 4, which is 1 minus 0.0625. So if a couple has 4 children, the probability that at least one is a boy will be 93.75%. So you see that that's pretty high. The opposite would also be true. The probability of at least one girl would be 93.75%. And that's just because these two probabilities are the same, 0.50, 0.50. So I know that's a little bit confusing. If you do it a couple times and just follow these steps, the steps are the same every single time if it's one of these at least one problems. That brings us to the final concept in Chapter 4, which is all on probability. And we need to talk about a really important word in probability, and that word is given. When I say the word given, it means that I have extra information. And here's the notation for given. It's the probability of A given B. And you do this little bar to represent the word given. And so usually I find that it's easier to understand this if you do it backwards. So what this is saying is, what is the probability of A happening given that B already happened? Okay? What's the probability that A happened given that B already happened? So kind of B happens first before A. And so that's why it's a little bit backwards. It's a little confusing. B happens first, then A happens. And you can also flip it. So what's the probability that B happens given that A has already happened? And really what this does is it shrinks our sample size. And so you're going to see what the effect of this is, that it's going to shrink our sample size. As I just said, when we have a given, we can eliminate some of our sample because we know that that sample isn't possible any longer. And so we can eliminate some members from our sample size. And I think it will make sense when we do some examples. So we talked about independent and dependent events. And here is where we bring that to its conclusion. Here's how it's harder to calculate dependent than it is independent. If two events are totally independent, then the probability of both of them happening, you just multiply their probabilities together. And we've done that a lot already in this chapter. We just took, the traffic light and whether the store had the item. Those two have nothing to do with each other, so we can just multiply their probabilities together. However, if A is dependent on B happening, and this is what we've already done with the marbles, where we took a marble out of the bag and didn't put it back, then the calculation for calculating the probability of both of them is the probability of A, the first event, just like before, times, and now you got to change it. It's the probability of A given that B occurred. Because B might not always occur. So if B affects A, if they're not independent, then we know that first we have the probability of A, that's just the first event, but we also need to multiply that. Instead of the probability of B, it's the probability of A given that B occurred. And so in symbols, here's what it looks like. The probability of A times the probability of A given that B occurred. And I know that's a little confusing, so we'll do some examples. Somebody did an experiment to see if people were more likely to spend money if they had quarters versus dollar bills. And so some students were given quarters and some of them were given a dollar bill. And we wanted to know, did they keep the money or did they purchase the gum? And so maybe people like to get rid of quarters because they're annoying, but people like to hold on to the bill. Maybe that's the question they were trying to ask. As usual, our first step is to find the totals, and so hopefully you see that I've done that. I just added up the rows, added up the columns, and found the grand total in the corner. Okay, so here's how you do a given example, and it's actually not that bad. Find the probability of randomly selecting a student who spent the money given that the student was given 4 quarters. Okay, so I'll read that again. Find the probability of randomly selecting a student who spent the money given that the student was given 4 quarters. Okay, the easiest way to do these problems is to do the second half first and then do the first half. So here's what I mean. Anything after the word given is information that we now know. So we now know in this example, the student was given 4 quarters. The student received 4 quarters. So that means we're only looking at this row right here. We're only looking at the top row because we know that the student was given 4 quarters. So we're not even looking at the dollar bill students anymore. We just shrunk our sample size. So do you see how I just made the first row bold? We know the student was given 4 quarters, and so we shrink our sample size to only those students when we're doing this. So now that we know that, what's the probability that they spent the money? Or in other words, what's the probability that they purchased gum with the money? So that probability is going to be 25 that they purchased gum divided by the shrunk total of 35. And that's how you do it. So first you shrink your sample space to only the people you're looking at, in this case the people with the quarters, and then you ask the first half of the question. Find the probability that they purchased gum. And so that's how you get 25 over 35. Feel free to rewatch this if you don't quite understand what happened. We'll do some more examples as well. Here's the next example. Find the probability of randomly selecting a student who spent the money given that the student received a $1 bill. Once again, when you see that magic word given, anything that follows the word given is information that we can know is true. And so we only want to look at people with the $1 bill. So look at your sample and shrink it. Do the second half first. Shrink it to only people who had the $1 bill, because that's what we're given. The student was given a $1 bill, so we're only looking at this row. Now that we did the second half, now go back to the first half. Find the probability that they spent the money. So of these 44 who had the bill, 14 spent the money out of the 44 who received the bill. And so that probability is 14 out of 44, which gets you to 31.82%. Okay, so you can see how that might be an interesting comparison. So in the previous one, if they were given the quarters, 71% spent the money. But if they were given the dollar bill, only 31% spent the money. So that's evidence that maybe people don't like quarters and just like to get rid of them. This is certainly true with credit cards. People are much less likely to spend as much with cash than with a credit card, because with the credit card, you don't see money being lost. But with cash, you can physically see your money going away. So actually, people spend less if they have cash than a card. One last example. Find the probability that the student was handed a $1 bill given that they purchased gum. This is actually a little tricky. It's not the same thing as the complement of the previous one. This one was find the probability they bought gum given that they had a bill. This is find the probability that they had a bill given that they bought gum. And you're going to notice that it has nothing to do with 31%. It's not the complement, it's not related, and you're going to see why right now. Once again, we look at the second half of the statement. What do we know? We know that they were given gum, that they purchased gum. So look at our table, and who are the people that purchased gum? You can see that it's only this column. It's only this column right here. These are the ones who purchased gum. And so we know that because it's after the word given. And so the only people we're looking at this time is a column instead of a row. So you need to be careful. Sometimes it might be a row that we're looking at. Sometimes it might be a column. Now we want to find the probability that they had a $1 bill. And so you can see that in this column of people who purchased gum, 14 received the bill, the dollar bill, out of 39. And so that's how we, calculate the probability. The probability that they were given the dollar bill, given that they purchased gum, is 14 out of 39, and it's 35%. So you can see that because it's a column instead of a row, it's a completely different calculation than the previous one. So just be careful with that. If you have any questions on this, please email me. Remember, the words after the word given, shrink your sample space to only probably one row or one column. So do that second half first, then answer the first part of find the probability of whatever divided by that total of that row or column. And again, you see the value of finding all the totals around the edges, because it makes this process a lot simpler. We only have a couple examples left and then we're done. Here I have a table of the lie detector test. Again, we should never trust lie detector tests. As usual, we're going to find the totals, which I've already done for you. And the question asks, find the probability that the subject lied given that the test had a positive result. Okay, meaning that the test said that they lied. So you can see that this is good for calculating false positives or calculating false negatives, or seeing if the machine worked or did not work. So here's the word given. That's your magic word for conditional probability. So we look at the second half of the sentence and it says the test yields a positive result. So we know for this question that the test had a positive result. So that means I'm only looking at, are you looking at a column or are you looking at a row? Well, here's where it says positive test result. So that means I'm only looking at this row right here. And so you can see that I shrunk the sample size to only this row. That's the given. It shrunk our sample size. Now it says find the probability that they lied. And so 36 out of the 51 lied. And so that's a 70.59% probability. So that's the probability that the test worked correctly in spotting a lie. It was a positive test result and the person lied, so that's a 70% success rate. Not very good, especially if there's a lot riding on the test, I have to tell you. One final example. Find the probability that the subject had a positive test result given that the subject lied. Okay? This is a slightly different question than the previous one. What's our given? Our given is that the subject lied. So we know that. We know that the subject lied, and so is that a row or a column? Well, here you can see it says subject lied, so that's a column. We're only looking at this data in the given. Now it says find the probability that the person had a positive test result. So we can see that once again that's 36, except this time instead of dividing by 51, we're going to divide by 62. And so it's a slightly different total, giving us a slightly different probability. And that's the end of chapter 4. And so hopefully these conditionals are making sense, and the word given and how it all works. If you're confused, please email me. And thank you so much for making it this far. And hopefully after this, we'll be back on track for the rest of the class. So thank you, and I look forward to seeing you on Friday for chapter 5. Bye-bye, everybody.